I think we can start the section. In the following hours, there is two sessions regarding to the XenGT. And XenGT is a graphic visualization technology and useful on the Intel graphic processors. So here is the first session is the live migration support for vGPU. Okay, so I will have the several agendas. The first, since I will introduction the GPU visualizations and what is the vGPU live migrations. And I have a very simple introduction on what is the vGPU resource we have, and with the highlight features what we have now for our GPU live migrations. And I have bring very short videos to give people say what kind of live migration currently looks like. And then I will go into the technical side. What is the challenges we have? So it's better now? Oh, okay. Okay. Maybe I need to hold this one. Okay, yeah, this is much better. Yeah. In the second part, I will go into the technical details. So, what's the challenges we have to migrate a vGPU instance, and how we overcome these challenges, and in the end, I will provide some data. So currently, what is the data we have, and have a summaries. So for GPU visualizations, this is a very simple introduction on the usage case. Basically, any like the workload with the 3D or 2D workload in a guest site, so you need GPU visualizations like the remote VDI usage model, especially currently on the cloud or the data center side. The medium processing. More of the real-time processing are trying to using the GPU side to accelerate the decoding and transcodings. So this brings the new usage model for GPU visualizations, and also like the remote CDAs, and also like the 2D or 3D office productivities. For example, you have like many VMs, and every VM like open like the explore browsers, and the browser will maybe need 2D renderings. So that is using the GPU accelerations instead of the CPU side. So XenGT GVT-g, we also call the XenGT. This is our solution to provide the Intel processors to have GPU visualization capabilities. So this is XenGT architecture. It is mediated the pass-through solutions. So if you have attended the Zen Summit like the last year or maybe last year before, and this is a high-level architectures you maybe already saw several times. So basically, I will not go into details, but the one thing to mention here is that we maintain a vGPU instance in our device models. And basically, to support the live migration is to support the migration of this vGPU instance. So, so what is the mediated pass-through here? Basically, we trapped and emulate the most of the resource, like the MMO resource, like the page tables. We trapped and emulate. So this is maintained the status here in the vGPU instance. And for the performance critical resource like the graphic memory access, so these are directly passed through to the hardware side, the red path here. XenGT, and we also call the GVT-g, also called the XenGT. This is mediated pass-through solutions, and this is very essential design that to support live migrations. So here is I listed several GPU visualization solutions. So like the left side, the first thing is typically like a vGPU pass-through solutions. typically there is several hardware models in the hardware level, and like the manager tools, or maybe the hypervisor, like the library something. It assigned one of the GPU core to a dedicated VM, and then the other VM submit the workload to the hardware, and totally the status maintenance was totally owned by the hardware. So in this case, so the vGPU instance, or maybe the hypervisor layer, or the management tools are not able to know the details of the current status of the GPU status. So this is very difficult to migrate this workload. Just for example, if there is a register which is write only, cannot read. So in this case, we cannot get this register informations, just read back the registers. So you don't know what is the current detailed status of these register levels. So you're not able to migrate to a target site. There is another typical vGPU instance, vGPU solutions is SROV solutions. So basically, there is a GPU PF model in the hardware level, and there is several VF models, and manager tools assigned one of VM model to one of the guests, and that guest dedicatedly owns this VF's core, submit workload to these VFs. And again, this is essentially very similar to the pass-through case, and actually it is the same as the pass-through. So the same problems, you don't know the details information on what is the current status of VF models. So this is also very difficult to pass through. And now going to the GVT-g solutions, because this is a mediated pass-through solution. So most of the resource we trapped and emulate in our device model here. And the migration is more like to migrate this via vGPU instance to a target site. And we also need to take care about the pass-through case. Mostly it is like the graphical memory access. So we need to take care of the graphical memory migrations. So here is the three typically GPU virtualizations. Currently, we already have a prototype code for the GVT-g live migrations. So here is the highlight features. The first thing is the GVT-g is an open source project. So you can get every line of code in public, and we have released every 3 months, quarterly, so you can get the latest code. And vGPU live migration follows existing hypervisor migration flows. That means you don't need to install additional software or libraries to support this. It's run just as now. And more important, currently our design is to seamlessly migrate workload. That means if there is a 2D, 3D, or medium workload is running in a guest, then this guest will migrate to a target site. The guest will not notice anything, and there is also no like the data loss or something. For example, if you have median decoding 100 frames in a video file, and this guest was migrated to another server. In the another server side, you get the same like the 100 frames, and this is identically same. There is no data lost, something. Currently, GVT-g is support Linux guest and also the Windows guest, Win 7, Win 8, and Win 10. For the timings, GVT-g live migration current service downtime is latency is around 300 milliseconds. It based on the 10 gig network adapter. It is designed with 2 gig memories and 512 mega graphic memories. The total migration time should be around like 1.7 seconds. So Let's see a video on what is current live migration looks like during 3D workload runnings. You can download the videos on the YouTube. It's okay. I see. We have prepared 2 identical machines, machine A and machine B. Yeah, now this is one of the migration. Machine A is there is only one guest is running the Tropic 3D workload, and will migrate from A to B and then to B to A, and every around 30 seconds. So the guest configuration is 2 gig system memories with the 5 and 12 mega graphic memories. So you will say it's like a seamless migrate from machines between different machines. So now it's about to migrate to the target machine B. Yeah. So you can notice there is around time gaps like the around 2 or 1 second, but the service runtime is around 300 milliseconds. Okay, let's go to the. So now already have understand what's current like machine looks like with 3D workload runnings. So now we can go into the technical side to migrate a vGPU instance. So what we need to do and what's the challenges. The first thing is we need to understand what is inside with a vGPU instance. Before understand that, we can go into details of how to migrate this resource. So since the GVT-g is a mediated pass-through solution, so we mark the different resource with different colors, and to migrate this resource with the different policies. So first thing is the yellow part. This is including the MMO registers and graphic page tables. We call it the GTT page tables. And these resources actually are trapped and emulated in the graphics in the guest side. And the green part we call is the pass-through region. This is the graphic memories. So the guest can once the guest are done with the render engines, so it can access these graphic memories directly without interview from the hypervisors. And the last part is the render engine side. And render engine is kind of the engine that take the 3D workload, 2D workload, and medium workloads, and almost everything in these render engines. And he will read the page tables and access the graphic memories directly. But render engine on XenGT side, it is time slice partitioned. So in a particular time, this engine was assigned to one of the guests. And that guest will run in his workload, and after like the 1 millisecond or 10 milliseconds later, and this render engine will yield to the other VMs, and other VMs will begin running his workload. So this is basically what is inside of a vGPU instance. Now the challenge is, so when and how we migrate this resource. As I just mentioned, there is MMO registers, graphic memories, and also like the render engine status. So typically, a QEMU or a standard like the migration frameworks will have 3 stages. First one is the per copy stage, and then is the stop and the copy stage. And the last is the resume stage. For per copies, we actually the same as like how we migrate system memories. So here we will check the GPU dirty pages. So any GPU graphic memories will be referenced by the GPU hardware. We will mark it as dirty. And then we will treat it as like the system memories dirty page and migrate to the target site. And once we run several runs, and then we will do the advance in the stop and the copy stage. So in the second stage, the copy and the stop and the static copy stage. In this stage, the vCPU is already stopped, and we will like remove the GPU scheduling for that specific VM, and then we will save the render engine status. We will try to migrate the graphic page tables at this stage. So after we do everything here and in the target site, we will resume one by one of this resource. Of course, we need to edit the vGPU instance into the scheduler again. So as we already identified this kind of resource, so here is the different policies we did to migrate this resource. The first thing is, as I already mentioned, for the registers, actually we are doing very simple. We copy to the target site, and we restore in the target site. For graphic page tables, we actually copy to the target site, and we do the shadowing for the target. And the graphic memories, it is same as what we did for the system memories. We check the data pages. Yeah. The data page is the graphic page, and then we copy to the target site. So for the last thing is the contents of a render engine. These things we actually do very similar, like we create the scheduler in the target site. So why a render engine could be as like simple as graphic memories we did. We can keep these questions, and in the later slides we will introduce why we just simply like to do what we do to migrate the render engine status, like the graphic memories. So here comes our design and the solutions. Okay, first thing is how to migrate the guest GGT page tables, guest graphic tables. So I just mentioned graphic page table is very similar like the CPU page tables. So we do the copy the entire table to target site, and we do the shadowing in the target site. But here we need to do one more thing is we call is graphic address rebasing here. We know for example, we have several several guests. For example, the VM1 and the VM2, and each VM takes a several range of the graphic memories. For example, 512 mega each VMs. So from the VM's point of view, he gets the resource already starting from 0. So here I will get the program the GPU commands. For example, he will try to access the GPU address 0. But in the hardware level, in the hardware point of view, in the GVT-g side, we will always partition the GGT table into several parts, and each gets on one of the parts. For example, for the VM0, he takes the range from address 0 to, take an example like the 512 mega. And the next is for the VM1, and next is to the VM3. And then this is because our design, the way we must choose static partition the GGT tables. We have I have the last sessions discussion on this, so we can to understand why we must to have static partitions. But here I just need to understand to know that this is we need to do to the static partition. So here. VM1, his graphical memory range starting from 0 was rebasing to graphic address A. So here comes the problem is every GPU commands already provided by the drivers. Before it was submitted to the hardware, we need to do the rebasings. We need to modify this address to address A, starting from address A. So here comes the migration for the GPU page tables. So simply summarize is 3 steps. we copy the entire table to the target site. We create the scheduling for the GPU page tables. And then we do the graphic address rebasings. After migration, it's again rebasing to new address like the B. So this is how we handle the graphic page tables migration. So now come to the pass-through resource. This is the graphic memories migrations. Again, graphic memory is very similar to the system memories, and so the migration policy is also very similar. In the per-copy stage, we will check the 30 pages and we copy to the target site. And in the second stage, in the stop and the copy stage, we migrate the remaining 30 pages, and then resume in the target site. So here comes the problem: is the Intel GPU page table do not implement with dirty flag or accessed flag. So this is our big problem here: is you can only know the page what potentially will be referenced by our GPU hardware, but you don't know when and how it was accessed. It was written or it was only read. So currently, a very simple solution is we'll just copy all these potential page to the target site. This is to make sure the correctness of the migration process. Of course, here is our optimizations we need to do in the futures. So left side is just a very simple introduction on when we do the memory migration to the target site, we copy the entire of this contents to target site, and we create the scheduling with this target machine address. So here goes into the graphic memory migrations. So now finally, it goes into our render engine status. So how we migration our render engines? As we just now we introduced, migrate our render engine status is very similar like to how we migrate our graphic memories. This is because Intel GPU hardware is context-based. It is context-based. That means hardware will not know the workload is coming from either way coming from hardware, coming from VM or coming from different process. Basically, every workload have his context. For example, like the render context 1, 2, 3, and hardware actually will not care. It is coming from VM guest or it is from the processors. So basically, the render engine here is he will load the context, start to execution the context workload, and before he switch to next context, for example, the context 3, he will save the render engine status, every status into the context 2. So here, the context itself is already completely stored, all the hardware status. So the migration of render engine status is become very simple. We just choose a write point, for example, here, we push the contents to the hardware engine, let the hardware engine to complete his current workload. He will save his context status into the complete context here. And then we will migrate all of these contexts like this complete context, also the pending contents to the target site, and push the contents to the target hardware. Of course, these two hardware need to identically same, like the cache configuration, like the EU numbers, everything need to be the same. So by this way, by nature, context was migrated to the workload was migrated to the different servers, and the context itself is located in the graphic memories. So migrate render engine status is to migrate the context, and the migrate a context is actually is to same as how we migrate the graphic memories. Okay, current status. Currently, GVT-g migration feature is an experimental feature. It supports both KVM-GT and XenGT. Currently, it supports Broadwell and Scalic processors. And benchmarks we already run. For Windows case, we run the Heaven, we run 3D Max, Tropics, and also we run the median transcoding and encodings. For Linux side, we run the Lightmac and 2D workloads. Qualities, currently we are able to run like the overnight testings and migrate the same VMs. Currently we only can migrate the one VM. For example, there is identical two machines that we can migrate the same VM back at the false overnight every 30 seconds. The tiny, as I already mentioned in the previously, is the overall total migrating time is around 1.7 seconds, and the service downtime is around 300 milliseconds. The two machines, the network is the 10 gig and adapters. The guest memory is 2 gig, and the graphic memory was assigned 5 and 12 mega. So, if there is a guest need to run the 3D or 2D or media workload in a virtualization environment, then GVT-g is one of the choices. Furthermore, you want to support live migrations, I think the GVT-g is the very good choice to try. So here comes our several resources. The first thing is our GVT-g project website. You can get almost every document in this site. And also here is the document list. And the third link is the Intel IDF presentations, which I presenting with the media and cloud usage with the GVT-g demos. So also we have the previous summit on 2015 and 2014, introduction to XenGT GPU visualizations. Okay. Yeah, here is my introduction to the live migration for the XenGTs. So questions?
Does this work? So you talked about how you can't track dirty bits for GPU memory, right?
Yeah.
But what about DMA that the GPUs do in the system memory while you're doing the pre-copy? How do you track dirty pages that occur because, for instance, the GPU is pushing data in the system memory?
GPU access the system memories when he running the workloads, but we choose the right time to migrate. The time is the GPU hardware is idle, so he will finish his workload, current workload. So the GPU hardware will not reference any graphic memories. So I would say in the previous pages here. So we will first stop the vGPU schedulings here. So there is potentially there is no workload submitted to the GPU hardware.
Right, but at the start of the pre-copy, right? So you've got 2 gigs of RAM, right? Let's make that a much bigger chunk of RAM, right? Let's make it a reasonable amount, like 32 gigs, right? So it takes an extensive amount of time to move it over 10 gig, right? Meanwhile, you're running a video encode, right? So you're shipping data into the encoder and it's pushing it back to system memory. So it's dirtying system memory pages, right, via DMA, while that pre-copy is going on.
Okay.
So how do you know which pages to go back and recopy at the end of the pre-copy phase? That's what I'm getting at.
This is our problem. Is the currently we don't have the dirty bit and the access bit. So as I mentioned, this is our problems here. And what we did is actually we copied the potential pages. And the current we did is there is no per copy stage here. As we know, these pages will always be copied in the stop and copy stage.
Okay, so you're copying the entire system memory of the guest.
No, not the entire. This is the graphic page tables that potentially will be accessed.
Okay, so just the subset that's mapped by the GPU page tables.
Yeah,
okay.
Subset, yeah.
So you showed migration of a 512 meg frame buffer, right? If you had a mix of different frame buffer sizes, when you migrate the GTT, are you able to deal with fragmentation of that GTT address space or do you have to does each VM have to land in a contiguous range on the target that it's being migrated to?
I guess I do not get the questions.
Can you go to the slide where you have the GTT page table migration?
Here.
Yeah, it's this one. So you see the when a guest VM GTT is migrated to the target,
this one.
Now maybe this is a simplification for the sake of the slide, right? But all the VMs have a contiguous range inside the hardware GTT view, right? So that works great as long as all the VM frame buffers are exactly the same size, right? If they are indeed contiguous. But if they were different sizes, eventually you can lead to fragmentation, right? Which would make it difficult to migrate from onto a specific target, right? If it doesn't have a contiguous range big enough. I mean, is the hardware capable of handling discontiguous ranges in that GTT view?
I'm not sure there is a fragment. I mean, Intel graphics will get the system memory. Actually, the graphic memory is going through the GTT page tables, and as long as this page table have this kind of range, a variable, then it is okay. For example, if there is a variable like this range is, for example, like the 512 mega, and then if there is a variable space in the GTT page tables here, then we can able to migrate. We don't care about system memories like the fragments or something.
Okay, this is my last question. So on CPU, right, we have CPU ID to help us understand compatibility between a source and a target CPU and whether or not you can run the same binary on each. Do you have any thoughts about how we approach that for GPU? How do we determine if a VM can actually run on a target GPU? In other words, how do we determine compatibility between?
Basically, currently our experimental code is we need identical hardware. So the vendor ID and the provider ID is the same for the same score of the GPU side. But eventually, I think as long as the Java will recognize the different GPU school is the same, then we are able to migrate. But as I mentioned, there must be like the same EU numbers, like the same cache policies.
Yeah, I just have a quick question. So just try to help me to understand of the GTT view, right? So the GTT view is basically just a flat VA space for the GPU. Can I say that? Is that the right understanding? Like you basically just try to find a continuous VA space and then land.
Intel GPU access the memories through this GTT page tables, and as long as this table, actually this table is more like more similar like the CPU page tables.
Right.
The difference is that CPU accesses the system memory through his page table, and GPU accesses the system memories by his GTT page tables. So I'm not sure I answered your questions, but
right. What I'm saying is this flat view, like it's a hardware GTT view, right, on the second column. Like, can I just say that just basically a VA space, right, for the GPU, and you just say, oh, this VM is taken from 0xa to plus 0xa plus 512 megabyte. That's his VA space. Then you just landed on the target VM in a different offset, but just still 512 megabyte.
Basically, it's like the send the whole thing is migrate to the target side, and as long as there is a variable space in the GT side.
Right, and also I think you're saying you are doing the page table patch up, right? You had to fix the page table stuff.
You mean the rebasing or?
Yeah, the rebasing, right? Yeah,
rebasing actually happened here.
Right, so that's I'm just curious because you said that the page table looks like just the CPU page tables. Do you have to fix all the levels, like all the PTE down to the PTE, or you have something else to do?
You mean the graphic page table?
Yes.
This is to actually software side. We prepare these page tables for for the each guest. So when we migrate, as I said, we copy the entire page table,
right?
The global page tables, and we will scan these page tables to do the rebasings. And so I'm not sure, there is no hardware levels to some kind of things.
So let's say in this the GPU page table, right? It points to some offset of the graphics frame buffer, like not from the 0 to 512 megabyte. It's a kind of shift to some offset, right? When you move to a different locations, do you have to patch that PTE?
I don't understand why is there relation the PTE? There is no PTE here.
Okay. No, because
this is the
because okay, maybe I just don't quite get what your page tables layout looks like, but okay.
How about this way?
So, one question I have is obviously, well, at the moment your architecture is based on a ballooning sort of system where you make the entire bar space of the GPU visible to each guest, but each guest is only allowed to use a small part of that and a particular part of that. Now it looks like you're talking about rebasing the address. So you're now saying that each guest is now only seeing a bar that starts from 0 and goes to 512.
Yes.
So are you introspecting on every GPU command now to rebase any GPU addresses that are embedded in that GPU command?
Yes, this is the we call this rebasing. So actually, if you attend the last year's XenGT presentations, we do the partitions here, and every guest will have the same tables, except there is a address ballooning.
Yeah.
So that VM address was not owned by this VMs; it was ballooning. So it cannot access. But now we limited the guest point of views. So the guest can only store his range of the graphic memories. Right. For example, 512 megas.
So each guest gets a zero-based.
You can zero-based. You can also any base. Yeah. But we do the rebasings, and we need to scan the GPU commands.
Right. Do you have an idea of how much performance cost you're taking in doing the rebasing versus the ballooning scheme?
Currently, I will say there is no performance penalty on this one, because in any way we will need to audit these GPU commands, because guest address or maybe the guest drivers or his commands were not untrust. So we will always scan these commands and get his address, make sure that this address was in his range. This is for the security consideration.
So the fact you audit was enough, obviously, that you had to touch every single address anyway, essentially.
Yeah, this is the same thing like the.
Yeah, and obviously a linear rebase is a pretty cheap thing to do, so that's cool. Thanks.
Oh, I guess we need.
If you could go back forward a couple slides to 17 again, I believe it was. Slide 17.
17, okay.
I'm still a little unclear about this lack of the dirty bit. How so in your pre-copy, stage, it says GPU dirty page logging, but you don't have a dirty bit. So I'm not clear what you're doing in there. And where exactly are you doing the copy of the GPU memory? Okay,
so I will say the design is we need to do the pre-copy here, and we get the range of the GPU memories. For example, we assigned the 500 mega to a guest, but he will only use the 100. So in this stage, our design is to minimize this range by the pre-copy stage. But here the problem is currently we don't have the dirty bit or the access bit. So actually we were not able to do that. So we have the consideration kind of further the optimizations. So we're trying to do the software way to get the dirty pages. But currently, basically, we do the copy of the graphic memories here, and this is actually nothing here.
That's a future wish list.
Yes.
Okay.
Well, I guess we need to get into the next sections. It's already like the time is already late.